All right, so quiz on Thursday. It'll be just the electricity of the body section.
It starts on 16.
Okay, 68 through 77. I got that okay? Electricity in the body. Any questions about it? What's that? Yeah, on Thursday. And then we'll have another one, probably. That'll give us, I think, 8 quizzes, right? I think this is number 7, so I'll just take those top 5 like I told you before. But we'll probably just get one more. Maybe we'll try to put in 2, I don't know. All right, so let's see, we were talking, remember we had several big ideas. Forces, that was Coulomb's law. Fields, those are related to forces, that's force per unit charge. We had potential, that's energy per charge. And then we also, now we're having potential energy, which is the potential for motion. So that if I have, say, 2 positive charges next to one another, and I let them go, they're going to move apart from one another. Or if I have a positive and a negative charge, they'll move towards one another. But the point is that they have a potential for motion, so they have potential energy. If they have, let's see, what were we doing? Oh, we can also talk about positive or negative work. We didn't really, well, no, we can have that with forces and fields, not so much potential. But we can talk about positive and negative energy. And if we have a positive energy, a positive potential energy, then you have to do positive work to bring them together. So if I imagine that I have a positive charge over here and a positive charge over here, in order to bring those 2 objects together, because they're repelling one another, I have to push on it with a force that's in that direction, and I'm moving it with a displacement that's also in that direction. So that's why when we have 2 like charges, they have positive work or positive energy. They have a positive potential energy. That works out with the equation here. Q, if both Q's are positive, or if both Q's are negative, I'm going to have to push them together. I have to do positive work in order to bring them together. On the other hand, if I have a positive charge and a negative charge, I have to hold those forces, I have to hold those charges back, right? It's like 2 dogs that are trying to go at one another, but you're on a leash, you're holding them back. And so I have a force that I'm pulling back in this direction, even though the displacement is in that direction. So whereas this is positive work, this is going to be negative work. When I have a positive and a negative charge, 2 dissimilar charges. So if these 2 charges have opposite charges, they actually do work on you. Or I can think of this as negative work because they experience an attractive force. When they're attractive, when the 2 charges are attractive, they're opposite. When their 2 forces are repulsive, they are like charges, either both positive or both negative.
So why'd you say negative work?
Negative work occurs when I have 2 charges, one negative and one positive. They're opposite charges. So these 2 charges, they would be attracted to one another. They would zoom towards one another. Like I said, like 2 dogs that are on leashes, and you're trying to keep them apart, or you're trying to just bring them together slowly. And in that case, I have to exert a force. This is me exerting this force. It's like the dog on the leash. I'm holding it back as it moves in that direction. And so I do negative work on this object. It has a negative potential energy, and I do negative work on it as those 2 objects come together. Okay? So you can remember if something has positive or negative potential energy just by looking at the equation. If both of these Q's are negative, it's a positive energy. If one's negative, one's positive, that's a negative energy. And if both are positive, it's a positive energy. We'll see, it'll come up a little bit later when we talk about the body and how things move from one direction to another in terms of their potential energy. So we'll revisit this a little bit later. Alrighty? Both force and energy decrease as the distance increases. Energy, that's potential energy. And be careful that you're differentiating between potential energy and potential. Remember, potential is an energy per unit charge, and potential energy is like what we've talked about already, like the potential for motion. So both force and energy decrease as the distance increases, though at different rates. What I mean by that is that the force is proportional to 1 over r squared, but the potential energy is proportional to 1 over r. If you forget that, they're on your equation sheet. They're just in the equations, right? F, K, Q over r squared, and potential energy is K, Q over r. And so the result of this is that if I double r, I have the potential energy, for example. Whereas here, if I double r, I quarter the force. So that's what I mean by they decrease, but at different rates. Right? If I increase r, this decreases, but the force decreases by a larger amount. And so if I were to plot F versus r, let's see, what does it look like? It looks like this. Whereas if I plot PE versus r, it looks like this. It's a linear graph, not a quadratic function. Okay, so when D is very large, I'm sorry, I keep using R. I'll put D or R. When D is very large, both the energy and the force, well, what are they? If I let's say that potential energy is KQ over D. If I let D go to a really, really big number like infinity or whatever, just I let D get very, very large, what happens to the potential energy? If I have two charges and they're a certain distance apart, but then I move them further and further and further and further apart, what eventually happens to the potential energy that they possess?
It starts approaching zero.
Right. And eventually it will approach zero, or we'll just say that it becomes zero. That if D gets really, really big, and we say D approaches infinity, then the potential energy equals zero. And that's true also for the force. That if I make my denominator big, then the potential energy or the force becomes zero. So both U and F are very small. They basically go to zero. Charges move in electric fields. We've seen that. Remember, we saw the plates. One side is positive, one side is negative, and we'll draw an analogy later where this is like a cell was separated by a membrane. If I have, say, a positive charge here, it's going to move in this direction. And I can think of my electric field. My electric field runs in that direction. So charges move in an electric field because they're under the influence of other charges. This positive charge is repelled by these positive charges, and it's attracted to these negative charges. Charges move in electric fields because they're affected by the other charges. They prefer to move in the direction of decreasing potential energy. We've seen this already. And when I say they prefer, I'm going to qualify that as positive charges. They prefer, they do move in the direction of decreasing potential energy, like a ball rolling down a hill. Remember, we talked about a mountain. Here I have high potential energy. Down here I have low potential energy. And if I have a stone that's on the side of the mountain, that's a positive charge, it's going to roll down the mountain. But also remember that if it's a negative charge, it does what? What does a negative charge do? Does it roll up or down the mountain? Up. Okay, it rolls up the mountain, that's right. So a negative charge does the opposite of what a positive charge does. And so taking that analogy over here, this is the high potential energy side. This is the low potential energy side. So the positive charge moves from high to low potential energy. Okay?
So negative charge would have to be water or an animal, right?
Huh? What?
So negative charge would have to be water or an animal, right?
No. This is just an analogy. So I'm moving from high potential energy to low potential energy. Now if I have a negative charge, like think about these plates, a negative charge, it's going to move from the negative side to the positive side. All right, bless you. It's a very quiet sneeze. Okay. So charged particles in the body, when we talk about this, probably next time, they will similarly move from areas of high potential energy to low potential energy. Sort of tuck that idea away, and then like so when we get to ions in the body moving across cell membranes, we'll remember that. We'll describe that in terms of this motion from high to low. All right. Let's try this question. The one on the left. Alright, generally objects move in a direction in which their potential energy does what? Alright, let's stop at 30. 30. Okay, good. B is right. We'll move in such a way that our potential energy decreases. Right, we'll generally move from high to low potential energy. And the electric field is a measure of what? No, let's not do that question. I don't like that at all. Oh no, never mind. So I didn't read the whole thing. The electric field is a measure of what per charge? All right, we'll stop at 21. 21. Yeah, no, it's going to be D, force. So keep these big ideas. You'll certainly see several questions about them. Electric field is force per unit charge. Electric potential is energy per unit charge. So we have forces, fields, potential, and then potential energy. Forces is just a force, that's Coulomb's law. Fields are force per unit charge. Our electric field E is F over Q. And that's on your equation sheet, so if you forget, look on that. But make sure that you're familiar with your equation sheet, that will help you a lot. Potential is energy per charge. You can sort of remember that because potential energy, it sort of is related to our potential energy. And then potential energy is just energy, so like we've seen before, it's the potential for motion. Alrighty? Make sure you review those big ideas. They'll be on the test for certain. But you'll need to understand fields, our forces, fields, potential, and potential energy. Yes? Understand? You need to know those big ideas. They're important ideas. All right, so electric potential is a measure of energy per charge. And so we'll define it as U divided by Q. U divided by Q. And you remember, huh? No, Q is charge. Q is the variable you use for charge. So the unit for this is going to be the volt. That's like the volt that we have, like there's 120 volts in our outlet. It's a measure of energy per charge. And a volt is 1 joule per coulomb. Remember, joule, that was our unit for energy or work, and then coulomb is our unit for charge. It's measured in volts, and it's referred to in a variety of ways. So we can electric potential can be referred to as potential, or voltage, or potential difference. And they're all very similar or the same. Actually, potential and voltage are identical. So these two are identical to electric potential. They're just the same words that we use for an identical term. Potential difference is a little bit different. It's the difference between 2 points in the potential. So if I imagine I have a charge here, and then if I think about 2 points, I'll call this point 1, I'll call it A, and then this is point B. If I put charges at point A and B, like I pull out my positive test charge, I put it right here, I would say that it has a certain amount of energy per charge. And then if I put it over here, I would say also that it has a different amount of energy per charge. Where would it have more energy per charge? At point A or point B? Let's do that as a clicker question. Where does it have more electric potential? At point A? Oh, let's see. What did I do? I guess I started already. Okay. Not sure why I started it. Well, let's just go ahead and use this. So the question is, if I put a charge at point A or point B, where is it going to experience more electric potential? At point A or at point B? And remember, potential is energy per charge. So you want to ask yourself the question of, where is it going to have the most potential energy? At point A or point B? All right. We'll stop at 305. A is right. Very good. Why does it have more potential energy at A? It's closer, so it experiences a greater force, and so it has more potential for what? For energy. For what? For energy. Yes, it has more potential for energy, but particularly potential for what? When we talk about potential energy, that's the potential for motion. Right. So if I have an object, a charge here at A, whether it's positive or negative, it's going to have more potential for motion just because there's a bigger force involved. Whereas if I have an object at B, it's going to have less potential for motion. So I can describe the voltage. Let's say that A has a potential, an electric potential of say 4 volts, and B has an electric potential of 2 volts. Then we would describe the potential difference between A and B as equal to 4 volts minus 2 volts. Yeah.
Would you have negative?
We can have a negative potential difference, and we will talk about that. You do get in the neurons, you get a negative potential. We'll talk about that when we get to it. All right. So if I imagine that I have an object at A, a positive charge at A, it's going to move towards the 2 volt potential. It's going to move through 2 volts of potential difference. the potential difference between these 2 points is going to be 4 minus 2, or 2 volts. And if I put a positive charge here, it's going to move through 2 volts of potential difference. Often we'll call that potential difference delta V is equal to 2 volts. Because delta means a change in something. Okay? Again, an idea that's going to come up a little bit later when we're talking about potential in the cells. There are a lot of charges going on in the human body. So, since potential is energy per charge, we can develop an expression for the potential of a single charge. So if I have a charge here, I have potentials at these different points that are certain distances from that charge, and we'll call these distances D. D here, I'll call this D1, D2. What is the potential at that point? Kind of like with the field, remember with the forces you have to have 2 or more charges to experience a force. But then we said, what if we take one of those charges away? I still have the possibility of a force, and so I described that with the field. So I can have a field with only 1 charge. And in a similar way, I can also have a potential with only 1 charge. And I want to describe what is the potential at this point. Since it's energy per charge, E then is equal to U over Q. That's K, Q, Q over R divided by Q. And so my equation for potential of a single charge is equal to KQ over R. On your equation sheet, but you do need to know how to sort of be familiar with that equation. So if Q is positive, the potential is positive. If D is large, the potential is small. I'm sorry, this should be a D. I keep forgetting. We use D here. Small. If Q is big, V is big. Please note that it changes. I'm sorry, it's hard for me to. In my other class, we use R, which is sort of more standard, but your book uses D, so we're going to continue using D. But if I slip up and use an R, that really means D. Okay? Let's write that in an equation form just so you see it. If V is KQ over D, if D is big, that means V gets smaller. If Q is big, that means V gets bigger. If I have a big charge, I have a lot of potential around it. If I'm really far away from a charge, that means I have less potential. The forces are smaller, there's less potential for motion. This can be kind of confusing. We begin to get a lot of terms that seem similar. The equations all look very similar. But keep your head wrapped around those big ideas. You might want to put them on note cards. Potential, fields, forces, and potential energy. And just put them somewhere where you can look at them for a day or two. It'll help you to sort them out in your head. Okay?
So, is K a constant?
Yeah, K is a constant. K is the same constant that we saw in Coulomb's law. And we're not really going to use it as a number because we just don't do any calculations with these.
So when K goes up, nothing goes up?
K doesn't go up. K is a constant. So this is Coulomb's constant. It has a value of 9 times 10 to the 9th. That's Newton meter squared per Coulomb squared.
It's for that number.
No, you don't need to know it. It's a constant. Don't even write it down. You're not going to have to use it or anything. But it
So
is a
the only
constant
one that goes up on K times Q is the Q.
Right, or the D.
K doesn't do anything.
K is a constant. Yes, I mean it doesn't change. Okay, so often we are interested in the potential difference. We've already seen this. which is the difference in potential of two different locations. In fact, if you're doing circuits, that's really, if you ever looked at a circuit or ever measured anything with a circuit, that's all that you ever measure, is the difference between 2 points. So you ever used a multimeter? You know what I'm talking about? You might have seen one. It's a little handheld deal, and there's 2 leads on it. And if you want to know the potential between 2 points, you put the leads down to the 2 different points. Those are your points A and B.
I have a couple somewhere.
Not jumper cables, that's different. What's that?
But I have a couple somewhere at home.
Yeah.
Back in my radio shack days.
Electricians use multimeters a lot to measure voltages and currents.
Always carry one around.
Yeah, it's always good to have a multimeter. So if a particle moves from point 1 to point 2, so if I move from here to here, and let's say the potential here is 3 volts, and the potential here is 1 volt, what is the potential difference? It's going to be 2. Right, so delta V is equal to 3 volts minus 1 volt, and that's equal to 2 volts. All right? You can, this would be my initial, this would be my final. I'm sorry, no, that would be my final minus my initial. Thank you, Kate. It's the opposite. Final. And initial. So 3 minus 1. But look, you can also move in these directions. How would you move from 2 to 1? What kind of charge would move from 2 to 1?
Negative.
A negative charge. So if I had a negative charge, Kate, I haven't forgotten you. I'm going to come back to you in just a second. If I have a negative charge, it'll move from 1 to 2 volts. And in that case, delta V would be 1 volt minus 3 volts is equal to negative 2 volts. So it actually, because it sort of gets a little funky with our negative charges because everything's opposite. But it moves from an initial position of 3 volts to a final position of 1 volt. And so it has a potential difference of negative 2 volts. Don't sweat that too much, right? But I just wanted to point it out. It'll come up a little later. Okay.
Well, one question is actually confusing now. So you don't go from final minus initial?
Well, in the upper one, this was our initial, or this was our final. Excuse me. No. What's I doing here?
Why is
Yeah.
3 your final?
Y is 3 my final?
Yeah, you don't find that.
Yeah, what's going on here?
Shouldn't that mean your initial? I'm so confused. 'Cause that's
Yeah, I'm confused too.
That's just because it's closer and the initial's far away. So it's always your final.
No.
Be 2 volts.
No, this is my final. This is my initial. This is my initial. I'm sorry, guys. And this is my final. I had them right the first time. Yeah. So, you know, I'm starting here and I'm ending here. I'm starting here and I'm ending here. Initial, final. And so the green is going to be, no, that's not right. 1 minus 3. Put that here. No, it's different.
Well, what if we just took those words out?
Yeah, we'll come back to it, okay? I'm sorry, I'll have to look at it. I have something mixed up. Okay? I'll come back to it on,
Does it make sense without the words?
No, you have to have the words.
Proofs?
It's not terribly important for us, okay? Mm-hmm. Alright, so batteries are labeled according to their potential difference It's the difference between their two terminals. So if I have a 9-volt battery, that means that there's a difference between these two terminals. That have 9 volts here and 0 volts here. Or 9 minus 0. Yeah.
I just realized the real question I wanted to ask. So, if you had more than one potential difference, besides just 2 volts, the one closest would be the first one that you did.
No, it depends which direction you're moving. Are you starting here and moving to here, or starting here and moving to here? It's really your initial and your final positions. Okay? Alright. So, electric potential difference and potential energy, we're sort of going to start moving into a little bit of our body stuff. So, a charged molecule or atom it's an ion, right? You can have cations or anions. Cations are positive, anions are negative. Moves between two different points, perhaps, for example, across a cell membrane. And these are going to experience a potential difference, and then the change in energy will be Q times delta V. Because remember, delta V is energy over charge, or rather V is U over Q. So if I'm talking about a change in potential, then I'm going to get a change in potential energy. So that's where these deltas come in. So if I have a charge that moves across a potential difference, moves from one point to another, and it's either going to gain or lose energy. It's going to see a change in its energy. Okay. That's a cue. Hmm?
Delta potential.
What? What doesn't have potential?
No, delta potential.
Delta potential, yes. All right. I'm going to go down. Okay, so charges tend to move to lower potential. Right? Think about our mountain. They move from high to low potential. So charges tend to move to lower potential. So this delta U will tend to be negative. Then positive charges will move so that delta V is negative. That's a decreasing potential. I'll explain this in terms of the mountain here in just a second. While negative charges tend to move so that delta V is increasing. And that's positive potential. High potential, low potential, right? This is my initial potential up here. This is my final potential down here. I'm moving from a big number to a smaller number. So the small number minus the big number is negative. That's what it means that positive charges will move so that delta V is negative, or a decreasing potential. From here to here is a negative delta V.
So potential energy and potential are pretty much the same thing.
They're very similar, yes. But remember, negative charges will move the opposite direction. Negative charges will move in this direction. So negative charges will move so that delta V is increasing. They move from a low potential to a high potential. So they have an increasing potential difference. with me on this? You look excited about it. It's kind of important, as we'll see a little bit later when we get next time when we get into cell
It's
membranes.
like looking at the potential for potential.
Yeah, sure.
In that metaphor.
Here I have a positive change in potential for negative charges. It's possible to move charges so that their energy does increase. Because in both of these, their potential energy is decreasing, right? My potential for motion, my motion is increasing, but as I move from here to here, my potential energy is decreasing. Likewise, if I move from here to here, my potential energy of this negative charge is also decreasing.
That's not figured out.
However, it is possible to make the potential energy increase. However, this requires some source of energy. Like for example, if we take an object that's here and we want to increase its potential energy, then I add an extra source of energy to raise it up within the gravitational field. And so that source of energy is usually, a battery, or it can be other things, chemical energy. This should be gravitational. And so this energy in cells to move charged ions, so their potential energy increases. To give the ions actually additional energy. This comes from something we call the sodium-potassium pump. You might have heard of this, but we'll talk about it a little bit in brief later. The sodium-potassium pump. It's like a battery in your cells. It gives the charges energy. And so in a circuit, when we have a circuit, the battery is what gives our charges additional energy. It increases their potential energy. All right. So we've already seen a capacitor. We haven't really talked about it in terms of an electrical device, but it is an electrical device. And it's a device that separates positive and negative charges. Has a number of uses. It typically consists of two metal plates that are separated by an insulator. Hey, good morning. So when we draw a capacitor is very much like this. One metal plate and another metal plate, usually separated by less than a millimeter. Actually, we'll see a little bit later, I'll show you a video where a capacitor is usually these two metal plates are squished together with a piece of paper in between them, and then you roll them up into an electrical device that you can actually put into a circuit. No, it's different from a battery. Capacitor is quite a bit different from a battery. A capacitor by itself doesn't do anything because it's just two metal plates. It's what we call a passive device, whereas a battery is an active device, that it actually will give charges energy. When connected to a source of potential, electrons travel from one of the plates to the positive terminal of the battery. So remember, negative charges, that's what we're talking about, negative charges, electrons, move from low to high potential, like moving up the mountain. Then that plate is positively charged. So what that means is that when I put a battery on this thing, negative charges will move. If I have any negative charges that are on this plate, they'll get up and they'll move over here. And then that leaves a positive charge on this plate. I just suck away all the electrons, and then those electrons will be deposited onto this plate. So it leaves me with a positive plate and a negative plate. And they're going to be equal in their charge. One's going to be equally positive and the other is equally as negative. Now, because that plate is positive, electrons from the negative terminal of the battery travel to the other plate. And then each plate has equal but opposite charges. I have a video I want to show you. This describes capacitors, sort of the history of capacitors and how we use them in circuits. It's really a little bit more than we need to use in this class, but it gives you a little bit of an orientation. It's from MakeZine. You ever look at MakeZine? It's like an online magazine, but it's for people that like to make things, like electronic circuits and other things.
I suppose the section on the side.
Let's see, let's go back actually. I realized what I was mistake. It wasn't actually a mistake, just wasn't really communicated. So back to this figure, y'all. That I am moving here, my negative charge is moving from initial to final. And that means that my delta V is going to be VF minus VI, which is going to be 3 minus 1 volt. So it's equal to positive 2 volts. Whereas here, my positive charge is moving from 3 to 1 volts. So the delta V for that one is going to be 1, that's my final voltage, minus 3 volts, which is equal to negative 2 volts. So we saw that a little bit later in the next page, that for a proton, or for a positive charge, I'm going to see a delta V that's negative. But for a negative charge, I'm going to see a delta V that's positive. And if we think about our mountain analogy again, right? My positive charges move from high to low potential. They roll downhill, so their final position has less potential than their initial position. So it has a negative change in potential, a negative potential difference. Whereas my negative charges, they roll uphill, so they experience a positive change in potential. Okay? Really the important part here is that you understand potential difference, that it's the final minus the initial voltage. And then also how the negative and positive charges react when they're moving from positive or high to low or low to high potential. All right, so capacitors, they're plates. These plates, yeah, Kate? What do you mean?
Can you go back a little bit?
I don't know where you want me to go.
Back to what you just did. Yeah, there. Okay, so I didn't touch the...
Okay. I'm going to take this away. All right, so the capacitance, if I have a capacitor, I can describe the capacitor in two ways. I have the area of the plates, and then I also have the distance between the plates. So what do you think will happen if I increase the area of the plates? You can think of capacitance. It describes the capacity to store charge. And what do you think will happen to the capacitance if I increase the area of the plates? If I make A bigger, will the capacitor's capacity to store charge, will it increase or will it decrease? If I make the area bigger, what will happen to the capacitor's capacitance or capacity to store charge? A, will it increase, or B, will it decrease? Now go ahead and click in. Jarvey, did you click in? Yeah, okay, good. All right, we'll stop at 32. Okay, so if I make the size of the plates bigger, I can just put more charges on them, right? Bigger plates means I can put more charges on them. And so that's going to cause the capacitors to increase their capacity to store charge. What do you think will happen if I increase the distance between the plates? So I have the plates here, and then I pull them farther apart. This one might be less obvious, but what happens if D is made bigger, the distance between the plates, to the object's capacity to store charge? All right, I'm going to stop here at 22. Okay, good. B is right. So if D is increased, C is decreased. If A is increased, C is increased. If I make the plates bigger, they can just store more charge. If I pull the plates apart, you can think of it, I'm spreading the energy around more, and so I can get fewer charges on the plates. Yeah?
So if D increases, C decreases?
If what now?
If D increases.
Right. Yeah. So the capacitance is proportional to the area, and the capacitance is inversely proportional to the distance between the plates. And so our equation is going to look like this. It's going to have A over D, but then there's another thing, a constant, which is our, it's called the permittivity of free space, but here we'll call it the dielectric constant. And E, or this epsilon, is equal to kappa times epsilon naught. So epsilon naught is actually the permittivity of free space. You don't need to know that. I'm going to write it here, but if you don't need to write it down. It's just a constant. It's related to that K value. It's very closely related to that K value. The K that we saw in Coulomb's law. And this letter, this is the kappa, the Greek letter kappa. It's not a K, it's a kappa. It has sort of a curlier K instead of a straight line. And it's called the dielectric constant. So remember you took apart the capacitor and there were two metal plates? What were between the two metal plates in that video? Anybody remember? What was between the two metal plates in the video? Paper, right.
So with his, it was plastic.
It was actually, yeah, so it doesn't really matter what is in between them as long as it's an insulator. You're right, when he made his own capacitor, he used two pieces of foil that were separated by a piece of plastic. But in electrical devices, usually the insulator that they use to separate the two metal plates is a piece of paper covered in wax. And that's called a dielectric. It serves a couple of purposes. The dielectric keeps the two metal plates from touching, because if they touch, if they're not separated, then the charges are just going to move between the plates freely. It also will increase the capacitance, the capacity of the capacitor to store charge. So kappa is the dielectric constant. It is determined experimentally. Means you just measure what it is. And different materials have different dielectric constants. Paper, plastic, wood, glass, those have different values for what kappa is. But it's always greater than 1. It always increases the capacitance. It's always, yeah, this is a 1 right here. The purpose of the capacitor, as I said, is to store charge. As a result, it stores energy that can be used for later. capacitors really have two purposes. One is to store energy. So in a circuit, you can store up energy. People that have cars with really big stereo systems, they'll often have lots of capacitors in those systems because they'll store up charge. And then when you need it for, say, like a big bass punch, then it will use that charge that's been stored up to deliver that to the speakers. So if you've ever seen a car like that, they'll have these huge capacitors. They look about the size of, I don't know, about half the size of a football. Capacitors are also used for timing circuits. Capacitors discharge at a very regular rate. When you put charge onto a capacitor, you can discharge it at a very regular rate. So whenever you have something that has a repeating action in an electrical circuit, like a flashing light, like your blinker lights, that's usually because of capacitors in the circuit. That you charge the light, you charge the capacitors, and then you discharge the capacitors.
Is that
Charge.
like cars have like more than one battery in them?
I don't know. I didn't know that. Yeah. All right. Yeah.
I've also often heard it described as being similar to like a battery itself.
You can use capacitors in a similar way to a battery. Since you brought that up, let me show you this video. So what he did is he takes this set of capacitors and puts it into his car. You know the way your car works is that you get electricity from your battery, but your car is also continuously charging your battery. That's what the alternator does, that it continuously provides an electric current to the battery that charges it. So it's a rechargeable battery inside of your car. And that way, when you stop the car, the battery is all charged up if everything's working properly. And then when you're ready to crank the car again, then you can crank it. It's a rechargeable battery. And so in a similar way, this capacitor is continually being recharged. So he's continually putting charges on these capacitors. And then when he stops, he has a fully charged capacitor. And then later when he comes out to get into the car, he can crank it up. Now, this is a problem if you want to use it in a car because the capacitors tend to lose charge. So if you leave your car for 2 or 3 days, then those capacitors are probably going to lose their charge. That's why we don't use capacitors, even though he's right that they're less polluting. You don't have as many chemicals, or really just 2 metal plates and an insulator all wrapped up. So they would be better, except that they don't work as well. But you can use capacitors to store energy. And that's what we use them for in electrical circuits.
To always turn your car all the way on. Like, you know how you can turn it halfway and it turns like the radio
Uh-huh.
on, but it's not anything. You just turn it into the battery.
Yeah, but you know, your battery can run for, I don't know, hours, things. All right. So when a capacitor is connected to a battery, the charge is equal to C times V. That's on your equation sheet, but C is the capacitance of the capacitor. V is the voltage of the battery. It's actually the potential difference between our two terminals. And then Q is the charge on that capacitor. So if I have a capacitor and it's hooked up to a battery, this is going to be the symbol for our battery. Say this is 12 volts. Say this is 3 farads. A farad is the unit for capacitance. Then our charge is equal to 36 coulombs. 12 times 3. Let me go back on here. Let me just give you the units here. So the units for capacitance is a farad, 1 farad, F-A-R-A-D. That's after Michael Faraday. He did some of the initial work with capacitors and described a lot of what we use today for generating electricity. And a farad, 1 farad is equal to 1 coulomb per volt. That's the basic SI units. And then the energy is equal to 1/2 CV squared. So if I wanted to find the energy on this, the potential energy stored on this capacitor, it would be 1/2 of 3 farads, that's C, times 12 volts squared. 3 times 144, what's that? 3, 420, or 32, 216, I think, 216 joules. That's the energy that's stored on that capacitor. Yeah, I think that's right. Okay?
I can't help but notice that the formula for U looks very similar to the kinetic energy.
It is very similar, and the reason is, don't write this down, but the reason is that when you take the integral of x dx, it comes about in calculus, but the integral of x dx is 1/2 x squared. Okay, and that's sort of where that comes from. All right, because you're taking an integral along the way, getting up to that energy. Yeah. All right. So, the sodium-potassium pump, that's like the battery of our cells, does not use a capacitor, per se, but there is a potential difference between the two sides of the cell membrane. There's also a capacitor of sorts set up between the two sides. It's not really a capacitor, but if I have a cell membrane and I have positive charges over here and negative charges over here, we can talk about it like it's a capacitor because I have this separation of charges, just like I do in a capacitor. And people in the medical sciences will talk about it as a capacitor. They actually assign a certain capacitance to the cell membrane. So if you know the capacitance of the cell, then you can calculate the charges that are involved. Again, in a later section, we'll get into the sodium-potassium pump and how all this business works, but we'll just sort of lay that aside right now and realize that we'll talk about our cell membrane in our cells in terms of capacitance because they have this separation of charges just like in a capacitor. All right, so some examples of capacitor use are flash on a camera, you store charge until you're ready to use it, until you have the flash. In those old cameras, remember the old cameras where you could actually hear the flash? Anybody ever seen like an old camera where like you hear a little buzz? That's the capacitor charging up. So you can have a flash on a camera, or you can have a flashing light. Anytime you have a regular, recurring electrical event, that's usually because of a capacitor. Because the capacitor charges, discharges, charges, discharges, charges, discharges. Keys on a keyboard. So if you have a keyboard, those are usually have capacitors in them. So if you have your keyboard, remember the capacitance is the area over the distance between them. So if you depress the key, if you depress the key, then that changes the capacitance of that circuit, and it tells your computer that you're pushing the R key because you're decreasing the distance between the plates of your capacitor, and that's a signal to the computer. So those are capacitors. We use them in all sorts of things. If you've ever looked inside of your computer, you'll see lots of capacitors. Those cylindrical things, sometimes they look like little flat discs. Fella Colin showed some capacitors in that video. Alrighty, let's see, we have 10 minutes, so let's do this current and resistance, and then that'll be all the stuff for the quiz. So you should review your notes for the quiz, but also review the textbook, that section. Remember guys, with the quizzes, that's a good time for you to practice for the exam. I really want you to do well on the exam, and the quizzes are a good preface, a good practice for you to do well in that exam. All right, current is the flow of charge, and it's going to be current, we'll use the letter I. I is going to equal to Q divided by T. That is a charge per unit time. And so we'll think of current, when we have a pipe, we'll think of it like charges that are moving along through that pipe. It's not exactly what's happening. Actually, it's more like energy moving through the pipe, kind of like a wave. But we'll talk about it as if they're actual charges moving through this pipe. A charge per unit time. Usually this refers to electrons moving through a wire. Though it can refer to any flow of charge. So like, for example, electrical lightning. Lightning will be talked of in terms of its current, even though it's not charges moving through a wire, it's charges moving through space. Like lightning. The unit of this is an amp. You've probably heard of amps before. Or ampere. 1 ampere is equal to 1 coulomb per second. All right, so that's current. A resistor is a device that resists the flow of charge. The current is the flow of charge, but resistance is that you're resisting the flow of charge. It's like you're slowing down the movement of electricity through a circuit. You can think about the resistor as a pipe with water flowing through it. So the resistance will be proportional to a couple of things: the length of the pipe and the area. It's length and the area. Is it more difficult to push water through a long pipe or a short pipe? Long pipe, right. So if L goes up, that means that the resistance goes up. Is it more difficult to push water through a narrow pipe or through a wide pipe? Like, for example, here, is it more difficult to push water through this part of the pipe or through this part of the pipe? The which one? The narrow, right. So if the area goes down, that means the resistance also goes up. So I have one direct proportionality between L and R, and one inverse proportionality between A and R. So our formula is going to look like this. First we'll have a constant. I'm going to go and write it. It's rho. I'll describe to you what that is. That's the Greek letter rho. And then I have L divided by A. Or if you want to write this, rho L divided by A. Either one of those are equivalent. Okay? Here, rho is something, it's a constant. It's kind of like with kappa, where we had that constant for the capacitors. Rho is the resistivity. It's different for different materials. So there's wood. It describes how much resistance this material will put up to electricity to flow through it. Do you think wood has a high or a low resistivity?
High.
Has a very high resistivity because electricity doesn't go through wood that easily. You can put electricity through wood, although usually it'll just, burst into flames. But it has a very high resistivity. So electricity doesn't flow through it very well. What are some materials that have a low resistivity? Steel. Anything else? Metals in general. Yeah, so metals, copper, steel, most metals have a low resistivity. That's why we use them in our homes to conduct electricity. Right? What kind of metal do we use in our homes? In our wires? Copper. Right, we use copper wires. So those are that have a low resistivity. The current is dependent on both R and V. So if I put the resistance big, what happens to the current? If R goes up, what do you think is going to happen to the current? Right. If R goes up, I goes down. And remember, voltage is a measure of energy. And so if I increase the energy to my electrons, what's going to happen to the current? It's going to go up too. So I will go up. So I is equal to, then, V divided by R. If V goes up, I goes up. If R goes up, I goes down. If I add more resistance, then I will go down. This is something called Ohm's law. I is equal to V over R. Sometimes you might see it as V is equal to IR. That might be the way it is on the equation sheet. That's just a rewriting of that equation. That's a pretty standard equation for electricians. Either a home electrician or somebody that builds electrical devices will use that a lot as they're designing circuits and analyzing circuits. Okay, yeah, that's sort of the way I usually write it. So for example, I'm also going to let you go here, but like for example, let's say that I have 12 volts here and 3 ohms here. If I want to know the current, it's V over R. That's 12 volts over 3 ohms. So it'd be 4 amps. Alrighty. We have a few questions. We'll do those next time though, but we will have a quiz and it'll cover all the way up to electricity in the body. And so I just want to warn you that I think if you haven't read this chapter yet, some of the concepts tend to be more complicated than what we've seen before. So please do read through the chapters carefully and be prepared for the quiz. I want everybody to make 100% on the quiz. Look for those big ideas. Okay? Is that pencil working for you?
Good enough.
No. Hey, y'all have a good day.
Got some more pencils.